Hello and welcome to topic 8, called Real Integrals 1. In the last topic, we derived the residue theorem, and this is a remarkable result that lets you compute a complex contour integral by finding the residues of the enclosed singularities. Over this topic, and the next one, we're going to see how the residue theorem and other tools we've developed throughout the course can be used to tackle difficult integrals of real functions. We'll do this by carefully constructing integration contours in the complex plane, where sections are related to the real integral that we wish to calculate. These calculations generally boil down to a bit of problem solving, namely hunting around for a clever way to construct your contour. In this first video, we're going to present a general recipe for approaching real integrals using our complex integration tools. We'll then show how this can be applied to real integrals containing trigonometric functions and go through some examples. So the intended learning outcomes for this video are that you should understand how complex integrals can be used to determine real integrals. And you should also be able to compute real trigonometric integrals using substitution and some complex integration techniques. Let's get going.
We're going to talk about something that we've implicitly assumed throughout much of this course, and that is analytic continuation. Consider a function, a complex function, with a valid series expansion in a circle we're going to call C0. I'll draw a picture. Where we have our real and imaginary axes. And let's say that this circle is centered at some point Z0, and it looks like this. This is our circle C0. Now imagine next that we pick a new expansion point for our function. And the point lies within C0. Let's call that point Z1. This can yield a series with a different circle of convergence. Which we might call C1. In the complex plane, let's say that this is our new expansion point Z1, and we end up with another circular region of convergence centered on that point, something like this. This is C1. This is called analytically continuing the original function into the new region C1. I'll write that down. We say that the original function has been analytically continued into the new region. And this is quite important terminology. And this is the critical result. It is a theorem, which I'm not going to prove, but it is a theorem that analytic functions that agree, in other words, they take the same values, on the intersection of their domains, and you'll recall domain is the input of the function, So it's a theorem that analytic functions that agree on the intersection of the domains are the same function. What does this mean more explicitly? Well, more concretely, let's say we have two functions. F of z and g of z, such that the following are true. Firstly, f of z is defined on a subset. Let's call it C of the complex plane. Secondly, a function g of z is analytic on a domain, and that's a range of input values, D, that contains the subset C. And the third condition is that this function g of z coincides or agrees with the other function in that subset. Okay, if we have these three conditions relating our functions f of z and g of z, then we call g of z the analytic continuation of f of z to the domain D. And this should be reasonably familiar to you because we've actually been assuming this for much of the course. We've already seen examples of this. And in those examples, we've been taking real functions for example, the exponential function defined for real variables, which is given by this expansion. This is analytic on the real line. And that corresponds to this first step in the conditions that we listed above. Our real exponential function is defined on the subset of the complex plane corresponding to the real line. And what have we done? Well, we've then been analytically continuing them to complex functions. Defined on another domain, namely the complex plane. And here, this is the exponential function, but with complex variables. And this is really important because it gives us a very useful way of approaching real integrals. And we can do that by considering the analytic continuation of the real integrand out to the complex plane. I'll write that down because this is the key of all that follows in the rest of this course. The take-home here is that this allows us to take a real integral. For example, it might be the integral between minus infinity and infinity of a real function. And we can then consider the analytic continuation. So this would be a contour integral in the complex plane of the complex analytically continued function f of z dz. And because we'll then be dealing with complex functions, we can use all of the tools that we've developed in the course so far to approach these contour integrals and relate it to the real integral. We can then use our new complex integration tools for example, the residue theorem. And we'll later see that branch cuts will be useful. We can use these tools and tricks to evaluate the real integral that we're interested in. Let's set the stage for the rest of this topic, and in fact much of the final topic, topic 9. We're going to be interested in real integrals. So quite generally, let's say we want to calculate some integral I, which is the integral from a to b, where those are real values of a real function. These limits may be taken to infinity as well. Now our general approach for applying methods from complex analysis to real integrals will be, and I'm now going to list some very general steps that we're going to encounter in different guises in the rest of this video. So our general approach is going to be a kind of recipe of steps to follow. The first step is going to be find some complex function g of z that is the analytic continuation of the real function f to the complex numbers. Then you're going to want to pick a closed contour C in the complex plane that includes some segment related to the real integral I. And a common example is that the contour in the complex plane contains part of the real axis. The next step is to decompose the contour C into pieces. So separate it up into constituent paths. That either relate to the unknown I or that we can compute. It might be some standard integral that you can look up. You'll then use the amazing result that we derived in the previous topic. You'll typically apply the residue theorem, or also Cauchy's theorem, to compute the contour integral g of z dz around this closed contour C that you've picked. The final step to wrap things up will be to combine steps 3 and 4. So you'll generally be able to equate the contributions along the constituent paths of the contour C to the solution that you get from the residue theorem or Cauchy's theorem. You'll be able to combine steps 3 and 4 to deduce the value of the real integral I. The best way to see how this approach works is to look at different types of real integrals and then go through a variety of worked examples. And that's what we're going to spend the rest of this video doing. I'll write that down. The simplest way to show how to use our methods is to present different types of real integrals and then work through a variety of examples. And we're going to go through a lot of different types of examples, and that really reflects the versatility of this approach that I've written down here. So far we've been writing a lot of text in this video. Now we're going to start playing around with some proper examples. The first type of integrals we're going to be looking at are trigonometric integrals. Here we'll be considering real integrals I that are generally of the form integral over an angle going from 0 to 2 pi of some function of the trigonometric functions sine and cos d theta. And here the real function f is finite and also single valued for all theta. First of all, we're going to want to analytically continue our real function, and we're going to do that by first making a change of variable. We're going to let z equal e to the I theta, and you'll recognize that as constraining ourselves to the unit circle. The differential dz is given by I e to the I theta d theta, and it's very important to remember that when you make a substitution you should check the limits and the differential, see how they change as well. This means we can rewrite d theta as minus I times dz over z. You can double check that for yourself. We also have, and you'll recall from our discussions way back in the first topic, that we can write cos theta as a half, and then e to the I theta plus e to the minus I theta becomes a half z plus z to the power of minus 1. And also that sine theta can be written as 1 over 2i, and then e to the I theta minus e to the minus I theta. You can also deal with multiple angles by taking, for example, cos n theta is a half z to the n plus z to the minus n, and sine of n theta is 1 over 2i z to the n minus z to the minus n. Okay, so returning to our real integral, we'll now be able to write it as I is, then we get a minus I from the differential. This is going to be the integral now around a closed contour, which by our substitution is the unit circle, and then our function is now going to be in terms of z. So sine theta becomes z minus z to the minus 1 over 2i, and cos theta becomes z plus z to the minus 1 over 2. And we finally have the differential has changed to dz over z. Now we can use our tricks from complex analysis. We can spot that by the residue theorem, we're going to have that I is this first factor of minus I, and then we have, from the residue theorem, 2 pi I times the sum of the residues at the singularities of f divided by z, and it's all of the singularities enclosed by the unit circle. It's f divided by z because of the differential. The differential added a factor of 1 over z. Okay, it's all well and good saying that. Let's put it into practice by looking at a couple of examples. First of all, let's consider I is the integral from 0 to 2 pi of 1 over 2 minus cos theta d theta. First of all, we want to quickly check that this function is finite and single valued. You can do that by noting that the denominator, 2 minus cos theta, always lies between 1 and 3. So you'll never have a 0 on the denominator, and therefore the integrand has no singularities for the values of theta that we're interested in. Let's apply our substitution. Setting z equal e to the I theta, we know that cos can now be written as a half z plus z to the minus 1. And plugging that in, our integral becomes, and looking at the line towards the top of the page, minus I, the integral around the unit circle of 1 over, and then we have 2 minus cos theta, which is a half z plus z to the minus 1, and then this is times dz over z. As a quick reminder, I'm going to draw a little picture at the side of our integration contour. It's the unit circle. This is our contour, C, where this is 1 minus I minus 1, and I. We can take the 1 over z inside to give minus I, the integral around the unit circle, of 1 over 2z minus a half z squared minus a half. Tidying this up a little further, we have 2i, the integral of 1 over z squared minus 4z plus 1 dz. And using the method of residues, we do indeed know how to compute this. We've gone from having a finite single-valued real function to a complex function that has singularities whose residues we're interested in. So for this contour integral, we need to consider the poles. We can do this by looking at when the denominator equals 0, and that means finding the roots of the denominator. Well, you can use the quadratic formula, and I'm going to write down the roots, but you can check for yourself that one of the roots is given by 2 plus root 3, the other root is given by 2 minus root 3. Crucially, we're interested in singularities that are enclosed by the unit circle, and it's easy to see that this first one lies outside our contour, whereas this second one lies inside the contour. I'll draw a little picture here again. We have the unit circle, and our singularities are z minus, which is enclosed, and z plus, which is outside our contour. And this is traversed anti-clockwise. This means that by the residue theorem, we have that the integral around the unit circle of 1 over z squared minus 4z plus 1 dz is going to be 2 pi I times the residue of our function that we can write as 1 over z minus the first root times z minus the second root, evaluated at z minus. You can check that this is a simple pole. And that means that we can use the expression that we derived in the last video of the previous topic. It's the limit as z tends to z minus of z minus, and then times our function. This is just 1 over z minus minus z plus, and you can check for yourselves that this gives minus 1 over 2 root 3. Finally, we can use the expression at the very top of the page to write that our integral, to remind you, this is the integral from 0 to 2 pi of 1 over 2 minus cos theta d theta. Analytically continuing, we found that this was 2i times the integral of 1 over z minus z plus, z minus dz. And by the residue theorem, this is 2 pi I times minus 1 over 2 root 3. And we reach our final answer, which is 2 pi divided by root 3. That's one example. Let's have a look at another. Let's consider the real integral I is now given by the integral from 0 to 2 pi of cos 2 theta over 5 minus 4 cos theta d theta. We're going to perform substitutions that we've outlined already above. And this is going to allow us to rewrite it as minus I, the integral, once again around the unit circle, of, and then cos 2 theta becomes a half z squared plus z to the minus 2, divided by 5 minus 2 lots of z plus z to the minus 1. And we have dz divided by z for the differential. This can be tidied up as I over 4, the integral of z to the 4 plus 1. So this is timesing top and bottom by z squared. Z squared, you have z minus a half, z minus 2, dz. Again, I'm going to draw a picture of our integration contour. We have the unit circle, and the integrand has singularities at 0, at 1/2, and also at 2. And you'll notice immediately that only the poles at z equals 0 and z equals a half are within the contour. You can check the order of the poles yourself, but I'm going to write down here that the integrand has a pole of order 2 at z equals 0, and simple poles at z equals a half and 2. As we've noted already, and clear from our picture, only the poles at z equals 0 and z equals 1/2 are within the contour. That means we need the residues at those poles. Let's begin with the residue at z equals 0. We're after the residue of z to the 4 plus 1 over z squared, z minus a half, z minus 2. Here this is a second order pole, say m equals 2, and you'll recall that from the previous video we showed that such a residue is given by this expression here. This is the m minus 1th derivative of z minus z0 to the m times f of z. Sticking that in, we find that this is the limit as z tends to 0 of d by dz, z to the 4 plus 1, and then the z squareds are going to cancel, and we have on the denominator z minus a half, z minus 2. And I'll leave it as an exercise for you to show that this equals 5 over 2. Next, let's get the residue at the simple pole at z equals a half. Again, using this expression, you can check for yourselves that this is the limit as z tends to a half of z to the 4 plus 1 over z squared times z minus 2, where the factors of z minus a half have cancelled on the top and the bottom. and this gives us minus 17 divided by 6. And we're basically done. This means we can write I, looking at the line at the very top of the page, as I over 4 times 2 pi I, and then the sum of the residues, 5 halves minus 17 over 6. This gives us the real number pi by 6, and we're done. We've calculated another real trigonometric integral using analytic continuation and the residue theorem. That's the end of this first video of topic 8. As a quick recap, we looked at analytic continuation, and we saw that it's possible to continue a function from the real line out to the complex plane. That means you can then use integrals of complex functions to calculate integrals of real functions, and I presented a recipe to follow to approach real integrals, and we looked at the first case of trigonometric integrals, where performing the substitution z equals e to the I theta allowed us to use the residue theorem in a couple of examples to calculate real trigonometric integrals. Next up is the second video. Thanks for listening.